When was it published? Some idea, roughly? Late 80s? Okay. Other ideas? Yes, you were right, in the 90s. And actually, this one is a little bit older than me. It was in 91. And so, fun fact, first fun fact, papers with similar name are still published. So now a paper in 2022, neural large neighbor search for routing problem, or this one solving routing problem with attention neural network. First fun fact. Second fun fact, if you pay attention to the name of the author, maybe here you can see Jean-Marc Rousseau. I don't think you know him, but maybe you know his son is the father of Louis Martin Rousseau. So even at that time, it was a really hot topic in the research community. Okay? And just to show you that learning heuristic with deep neural network, with neural network on machine learning is a very old topic. It's still unsolved. Okay? Okay, now how learning can be used to solve a combinatorial problem. So as it is a summer school, here also I would like to give you some advice of how you can dive into this research field. And one of the advice here it is a very nice survey from Yoshua Benjo, Andrea Lodi, Antoine Provost, that roughly explain 3 integration of learning for solving combinatorial optimization problem. I mean solving, not modeling. I will speak a little bit later on that, but here on solving. So roughly speaking, they identify 3 integration: end-to-end learning, learning to configure algorithm, and machine learning with combinatorial solver. And what is really nice, you can see that you have here a very, very nice summer school. You get example of each of them in the previous talk. And we also have related fields that are very interesting in this field, so learning how to model and also how to tackle uncertainty, for instance, with predict and optimize, constraint acquisition. So end-to-end learning. So here the idea, quite intuitive, the problem is directly solved using machine learning. So you have your TSP that is unsolved. You have a machine learning here that is trained using training data. And then you give your problem to the machine learning model, and the machine learning model will crash you the solution. And you can do the training with your favorite algorithm, supervised reinforcement, or even unsupervised. So that's end-to-end learning in the essence. OK. Now, with end-to-end learning, and Nando explained this the first day, we have a fundamental limitation, a main difficulty to tackle. So the machine learning, the goal of machine learning is to predict an output. And an observation of that is that with machine learning, with a model, we can do some mistake. 100% accuracy is not possible on the test set. Or it is possible on a training set, but generally speaking, when you have that, you have other issue. Let's say a very simple task, MNIST. So it's one of the most studied by a machine learning researcher. The best accuracy that is currently reported is roughly 99.9%. And difficulty here, even if we have a very good accuracy, is not perfect. We can do some mistake. And this is a real bottleneck for combinatorial optimization. I don't want to obtain a prediction that gives me an infeasible solution, or in some case, to lose optimality. And so the challenge here with end-to-end learning, how can we handle arbitrary combinatorial constraint? How do we handle constraint? How do we handle feasibility with end-to-end learning? And so here there are a lot of work on that. Another advice is to look into the survey of Nando end-to-end constraint optimization learning. And he gave some pointer during the first talk. OK? So second, I'm moving to the field of Lars, learning to configure algorithm. Here the idea is to augment the solver with valuable piece of information. So here you have your solver, and you use machine learning to help the solver before calling it. So you provide the solver with valuable information. For instance, you can select appropriate parameter for the solver. If I take Cplex, we have more than 70 parameters, so we can try to learn which one are the most useful for my given problem. Selecting a specific configuration when you want to compute a linear relaxation using interpol method or the simplex, or deciding if a preprocessing step must be done. OK? So here, it is learning to configure algorithm, but depending on which community you are, you have different names also. You can think also about automated tuning, portfolio selector, portfolio configurator. So there are different names for that. And what I like also very much with that is that often these kind of approach are complementary with other learning approach. You can use both. Okay? And also some related work, and also another advice to look the survey of Lars about that. That is quite recent. Okay? So I'm not working on that. I'm more working on that. Machine learning within combinatorial solver. So here we have two worlds. On one side, we have traditional solver, for instance, of constraint programming or branch and bound, that can provide guarantees, but sometimes it's hard to make it efficient because there are some non-trivial tasks inside the solver. And if you do only learning, only end-to-end learning, okay, you can get it's easier to use, but it struggles to get guarantees. And so here the idea is to use machine learning inside the solver in order to speed up the solving process. So just to give you a picture that I adapted from the survey of Yoshua Benjo. So you have the definition of your problem, and the problem is solved by the solver. So you can get the guarantees of the solver. And now, where is machine learning on that? Somewhere in the solver, you are in a given state. For instance, a node in your tree search. And in this node, what you will do, you will call your machine learning model to take a better decision. Okay? And this decision will be used for the solver to do another decision, and so on and so on. And so the idea here is to help the solver. What is really nice here is that the solver, even if you do a bad decision, a bad prediction, the solver will be able to recover from this mistake, as we do with heuristics that are not perfect. Okay? So example of what knowledge we can learn is learning to branch or learning optimization bound, and today I will speak about learning branching decision. Okay? And few work also about that, and Elias is one of the researchers working a lot on that for mixed integral programming. Okay? So that's one part of the picture, but I am not yet satisfied because I told you at the beginning that in intelligence we have different aspects. And here I am missing the aspect about reasoning, for instance. So here, okay, we can use our intuition. By intuition, I mean heuristic and search with trials and error. We have machine learning, so we have the aspect of learning. But reasoning, what can we do for the reasoning? Here, I would like to use logical reasoning also to improve my state, for instance. Also, I want this to be generic, not specific to a single problem, but to use this framework for many problems. And also, the cherry on the cake, I want this to be easy to use for end user. I don't want this to be only usable for experts. I want this to be usable for a small company, for non-profit companies, and so on. And so that's a little bit the holy grail of programming, and I think you see where I want to come. I will switch to constraint programming. So how can we do that? And the research hypothesis that we are following in my work is that I think that constraint programming can be used as an hosting technology for building this kind of hybrid AI. In a standard CP solver, you already have the model, which are kind of adaptation for different problems. You have the propagation, which is a very generic way to do logical reasoning inside the solver. You have the search, which is delivering a heuristic, so using your intuition to better solving. And what is really missing is the learning part. And so that's what we would like to integrate, learning inside the CP solver. But is it a task that is difficult to achieve? I won't say it is difficult because it's quite subjective, but what I can say in an objective way is that I have been working for that for 3 years, and I don't have a solution yet. So what I will present today is few attempts and where we are so far for this task. And I will begin here with one contribution of a paper of 2021, a paper of AAAI, where we provide a first proof of concept that combine reinforcement learning and constraint programming. So let's assume we have a combinatorial optimization problem that we want to solve. So we have some instance that we want to solve. First thing we need to do in this proof of concept is to cast this combinatorial optimization problem into a dynamic programming model. So like Walters explained yesterday, we needed to have a dynamic model, dynamic programming model of my combinatorial optimization problem. Why? Because, and that's the contribution of this paper, using this DP model, we are able to build at the same time a constraint programming model and use a constraint solver, and also a reinforcement learning environment. So from the same DP, I am able to build my CP model and my RL environment. And also, I have a synchronization with my state in CP and my state in RL that allow me to use, during the CP search, then a model that is learned with reinforcement learning. So how it is done? So in constraint programming, so it was implemented in C++ and G-code. For the reinforcement learning, it is in Python, PyTorch, and also deep graph library because we use graph neural network. So for the learning, what we do, we have training instance. For instance, in this case, we randomly generate it in order to train the model. And now, each time we have a state somewhere in my reinforcement learning environment, this corresponds to a node in my constraint programming search. For the learning, you can use any kind of algorithm you want. In this case, we use deep Q-learning or proximal policy optimization, but you can really use whatever you want. And what we learned is a value selection heuristic, telling you, OK, in this node, I want to branch on this variable. And for this variable, I will assign this value. And that's what we learn, which value I want to assign to my variable. OK? And for the search, we have three kinds of search with a different benefit. And I will show you afterward how does it work. OK? So that's a first proof of concept. Just a small example of how it is working. So here, let's assume I have a TSP problem to solve, and I am in my root node. So as I said, I need a dynamic programming model. And the one I will present here is the same that Walter explained yesterday. So here it is your current position. And here, this set here is the remaining customer to visit. So, OK, I am here, and I need to visit him, and him. In constraint programming, OK, I select one variable, and I have different options, my different value. So what is my next customer? And so what I do when my model is trained is I will call my model. OK, what do you think is my next customer? And in this case, my model that is trained tell me, OK, it is the customer 3. So now where I am here. And I have to visit still customer 1, 2, and 4. OK, I am in a new state, and I continue. Now I have 3 possibilities. I'm calling my model where I need to go. OK, go to 2. Great. I'm here, but you still need to visit 1 and 4. And so on. I continue. And then, oh, OK, here it told me to go to 4. OK, that's nice. I will follow my model. And then I continue, and OK. I am at the end of my tree. I am in a leaf, so I have a solution. That's what you will obtain if you follow only a heuristic or using end-to-end learning. But now, because we are in a constraint programming solver, what can we do? What we will do, we will backtrack. I can backtrack to recover from bad decision and trying to discover other solutions. So here, OK, I backtrack. I'm coming back here. OK. Here, I don't have other possibilities, so I continue to backtrack. So I'm going back here. And now I have my model. I don't have to explore it anymore because I know it. So I will explore the other branch, 1. OK, I'm going here, and then I continue here. I will go here, and here. I have a new solution. So I am able to recover from bad decision thanks to the CP search. OK? And also, I can use any kind of, in the solver here, you have propagation also that is done in order to reduce the domain. OK? So that's the first proof of concept that we have developed. In a more formal way, it is one of the 3 algorithms we propose in this paper. You will see it's very simple. You don't need to read it. I will go it with you. So we begin with a COP, constraint optimization problem, with a DP formulation. First thing we need to do is to cast your problem into a CP model. And this, it can be done in an automatic way. Then you initialize a search, for instance, a branch and bound search. Then, while the search is not completed, you will encode your current state as a state in reinforcement learning. You do that. You select a variable to branch. It can be following the first fail principle, for instance. And then for this variable, that's the interesting part, here, for this variable, OK, I will scan all the domain of my variable, and I will take what we call, it is a Q-value, will take the value that has the highest estimation given my model. So I take roughly the best value given by my model. Okay? And then I do all the CP stuff and so on. Okay. Seems to be a good idea, but does it work well? Actually, we could observe some signal of learning, so that's a good news, but it is quite inefficient. We needed to add few things in order to improve the performance, and that's something that can be done easily in a CP solver. So first, improvement that is quite, I would say, obvious. In a CP solver, when you backtrack, you are coming back to node that you have already visited. So there is no need to call again your model, in this case your graph neural network, to get the prediction. So you can cache some prediction and use what is in the cache in order to do the other option. So we use caching, and that's what you can see in the algorithm here. Here it is the cache, and if my state is in the cache, I will just take it, the prediction. Other improvement, that is something I like very much, is because we are in a CP model, here what you can do also is to use the tools that you have in CP. For instance, you can add a redundant constraint to prune more the search space. And that's something you can do, and that's what we did. We use redundant constraint to express some dominance pruning in dynamic programming. So the good news here, we have signal of learning. But we also have a lot of drawbacks. First, main assumption is that we need to cast the combinatorial problem into a DP, and it is something that is a little bit different with the philosophy of CP that we want, okay, we want to be able to model any kind of problem. No, here we are limited to DP. So for us, it was a main limitation. Also, the learning was disconnected from the CP solving. We did the learning, okay, with the synchronization of the DP, we know that it corresponds to a CP state, but all the learning is done outside the CP. So it means that we miss important information. We miss, for instance, information about the propagation. And also, another difficulty here, we need to build a model for each problem. In this case, we have experiments on the TSP with time windows, and so we need to build a graph neural network that takes the TSP with time windows instance for the prediction. We have another experiment on the portfolio optimization, and for the portfolio optimization, we use another architecture because it's not a graph. We use a deep set transformer. But so we needed to have a specific architecture for each problem, which is also not so relevant in the context of constraint programming where we want to be generic. And finally, some technical difficulty. Because we have the C++ code and the Python, we have some loss of performance between the back and forth. We use a PyBind to do the matching. OK. Seems that there are a lot of drawbacks. Can we do something? And here the idea that we had is we tried to embed the learning inside the CP solver and not outside. And the difficulty, we wanted to do that, but there was no, at the time, no available solver allowing to do that easily and efficiently. And the reason for that is that there is a friction with the CP solver that we wanted to be efficient, and also the machine learning support that is mainly in Python. So another contribution here, I would say a more technical contribution, is that we introduced a new CP solver making easy to integrate learning inside. We wanted a CP solver where any researcher can easily integrate a learning component on it quite easily. And when you build such an implementation, the first design choice that you have, which language do you want to use? And in our case, after many discussions and also considering a lot of different languages, we decided to opt for Julia language. Who knows Julia here? OK, great. So you already know that it's a great language. So few words about why we decided to take this language. It is simple to get on board and yet fast and clean also. It is an active community in both optimization and machine learning, and for us, it's something that is quite important. Because I am a computer engineer, I have a lot of language that I like a lot. For instance, I like the Scala language. But if I am speaking to someone more in the operational research community, they don't know Scala. They don't know how beautiful Scala is. They don't care about it. They want a language that they know, that is easy to use. Often, they don't know Scala and other language that I like very much. And so we wanted a language that can be appealing both for people in machine learning, but also in optimization. And we believe that Julia was the good trade-off for that. Also, it is a language that is quite young, and it is both a benefit because the community is very, very active on that, but also a drawback. There are a few packages, for instance, where we detected some issue on that, and we need to fix it by yourself. And also, we were joking with Tayas last day, no CP solver available, so no competitor. No, but we wanted also to fill this gap in the Julia because there are a lot of solver-based, more integral programming, conic, linear programming, non-linear programming, but there was nothing in CP excepting one solver that is not longer maintained. And to summarize the philosophy of Julia, it looks like Python, but it runs like C. OK? And then I can introduce, after Pineapple, CPerl for CP with RL, CP solvers that are using RL inside. So the goal here is really integrating this learning part inside the CP solver. The philosophy here, we don't pretend to build a solver that has the scope of G-code, for instance, or CP optimizer. The philosophy at the moment is to have a minimalist CP solver dedicated to use the integration learning and really to help researchers to integrate that. The project is open source. You can check it on GitHub, and it's still under active development by the team in Polytechnique Montreal. You have the link here, and during the lab, you will be able to play a little bit with it. And we also have another repo with the different examples, both with standard CP, so you can do also everything as a standard CP solver, but you can also integrate learning. OK? So next topic in this talk, I will describe the architecture behind CPerl. I will presenting few experiments on its performance, its current performance, and also the part that I think is the most important, identifying what is not working, what are the current challenges, and the possible future direction in this field. And so we have also a lot of different ideas. I will propose a few of them, but we are very happy also if you would like to contribute. OK? And what I will explain in the next slide, it is, roughly speaking, the content of two publications. The first one at CPIR that introduced CPerl, and the second one that will appear at CP this year. Question? OK. So here you have the main picture of CPerl. You can see three components. The constraint programming solver here, and a mysterious representation box, and also a box representing the learning. OK, constraint programming solver, generic representation function, and the learning agent. OK, let's go first on the constraint programming solver. And for that, actually, I will be quite quick, because Tayas did a great job the first day to explain to you what is constraint programming. And because the constraint programming solver is quite common, I don't have a lot to explain. So just a few general characteristics about it. The inspiration is from mini CP solver in Java that is developed by Pierre Chose, Laurent Michel, and Pascal Van Enterick. And so the idea here is to keep this minimalist aspect, but yet efficient. The data structure that is used is a trail-based solver, so without going into the detail, in a CP solver, you can have two ways of managing the information, either copy solver or trail-based solver. For a copy solver, the only one I know is G-code. When you are somewhere in your tree, you have information, and when you branch, you will copy all the information. In a trail-based solver, it's not the case. When you are somewhere in your tree, you have information. When you go to another node, you will add information, but also when you backtrack, you will erase this kind of information. So you only add what is useful to go to one node to another one. And for the modeling, also, we plan to build an interface with jump. So jump is a kind of mini-zinc for Julia. For the search strategy, here it is quite interesting, because the standard CP search is using DFS with branch and bound. That's the default strategy that you can find in a CP solver. But in our case, what do we want to do? We want to build a heuristic that we trust. And the question here is, is a DFS the best way to leverage a heuristic that we trust? And here I will show you that no, we can leverage heuristic in other way with other search procedure. For instance, using iterated limited discrepancy search. And also, when you learn a heuristic, you can also try to learn probabilistic heuristic. That's what it's done with policy gradient, for instance. And here, how can we leverage probabilistic heuristic? And for that, we have a new search that is interesting. It is the restart-based search. For the propagation, nothing really new there. We have a filtering for each constraint, and at each node of the tree, we execute the fixed point algorithm. So the fixed point, you take all the constraints, you propagate as much as you can, and you iterate until nothing can be pruned. And for the constraint, just to give you kind of sense of what do we have intention constraint, extension, so the table constraint, all different sum element, and currently the solver is compatible with the mini competition of XASP3 for TCR. But only the CP part, not yet the learning. And we do not have yet the result about the performance. OK. So for the modeling, you will play a little bit in the lab. So just to give you here what it looks like. So here it is how you will initialize your CP solver. So it's an example for the graph coloring. First, you have the declaration of the different variable. And in this case, for each node of your graph here, you will add one variable. So here you add one variable per node. And the domain is here the number of vertices. So without heuristic, we'll say, OK, I have 10 vertices. I have at most 10 colors that I can use. So that's my initial domain. So very, very easy here. Then I can add constraint. So for instance, this constraint is a symmetry breaking constraint that tell me, OK, my first node here, I will assign it the first color that I have, which is the color blue here. OK, so for x1, I give it the color 1. OK? And then for the edge constraint, that's the graph coloring part. It means that for each edges, so I have a loop here for my edges, I tell, OK, the two colors must be different. So really what you can find in a CP solver. And finally, the objective function, we want to minimize the number of colors. And so the goal here is to keep the modeling ease of CP. And also for prototyping, that's something nice also with Julia. You can use it in a Jupyter notebook. And actually, I discovered that the Ju of Jupyter is for Julia. That's something I didn't know before. OK? OK. Now, something more interesting, the search in Julia. We have different kind of search implemented, but I will show you the iterated discrepancy search, which is the one of the most interesting. But first, I will just a small recap of the DFS. So let's assume it is your tree search. OK. What the solver will do? You begin at the root node. You execute the fixed point. In this case, nothing is pruned. OK, you continue. You branch x1 equal to 1. You are here. You execute the fixed point. Nothing is done. You continue. Here, OK, you execute the fixed point. You branch. You prune everything. So no solution. What you will do, you will backtrack. You backtrack here. OK, I continue. I branch here. Fixed point. I prune this branch. OK, great. I continue. I have a solution. I continue, and so on. Then I do it until I have my optimality proof. OK, that's DFS. And so the question here is it the best way to leverage a heuristic that we trust? And the answer is no. Why? Because before going on this part of the tree, with the DFS, I will explore always this part first. But is it a good idea if I have an heuristic I trust? Not always, because if I'm taking this node here, what is the meaning of this node? So by convention, when I go left, it means that I trust my heuristic, because I take the first choice of my heuristic. If I take this direction, it means that I deviate from my heuristic. And so if I take this path here, it means that I have deviated from my heuristic only once. I just deviated only once from my heuristic. And so in here, I haven't deviated from my heuristic. So I just deviated once from my heuristic. And if I take this node here, for instance, here it means that I have deviated twice from my heuristic. One here and one here. And so the problem with DFS is that it is very difficult to recover from early bad decision. So the decision that you do at the beginning of your tree is very, very important. So you do not have a way to recover easily from that. And so the idea of a iterated limited discrepancy search is to allow you to leverage the best as you can heuristic that you trust. The principle is very simple. First, you do the search without allowing any deviation from the heuristic. So you will explore this node first. Then you restart, but you will allow only one deviation. So for instance, OK, I don't deviate, OK, I deviate once. I will explore here. OK, I don't deviate, I deviate one, I don't deviate. OK, him. I deviate, I don't deviate, OK, him. OK, I did for one. What I will do now, I will allow two deviation. And then the order of visit here will be something like that. Okay, and the last node visited will be this one where we don't trust at all the heuristic. We take everything that the heuristic do not recommend. Okay, so that's iterated limited discrepancy search. And of course, you can use propagation here, and you can also introduce some mechanism to avoid redundant work when you do the restart. Okay, so that's a good heuristic to leverage heuristic that you know. Yes? Yes, that's what is done in practice with a more elaborate implementation. Okay? So another kind of search is restart-based search. And this one is quite intuitive also. Instead of telling the model, OK, take this, this branch, you give probability instead. OK, I am 80% sure that it is a good decision and 20% sure that it is a good decision. And when you will branch, you will just do a roulette selection using this probability. OK? And you will also periodically restart to get other branch. But the question here, because here it seems to be only a Monte Carlo sampling, what is the difference? The difference is that you can still introduce some backtracking in CP. For instance, okay, let's say you sample this branch, but you will still allow some failure, some backtrack in order to explore similar zone. For instance, with some backtrack, if you allow only one backtrack, you will also explore this. And in CP solver, we have what we call the restart schedule that will tell you, okay, after how many failure I will restart. And something that is quite common in a CP solver is to use the Lubby sequence. So if you don't know it, it is the sequence that is here. And how to read it, it's each time, let's say, you will allow first one restart, then 1, 2, and then to compute the remaining part of the sequence, for instance here, what you will do, you will copy everything that is before and double the last number. So 1, 1, 2, 4. And then for the next part, we will restart like that, 1, 1, 2, 1, 1, 2, 4. So I copy everything that is here, and I add the 8 because I doubled the last number. So it's allowed to increase smoothly the number of failures that you allowed. Okay? So that's a way to leverage probabilistic heuristic inside ACP solver. Yes? All of them. All of them. At the end, you will restart like that. I allow one failure, then 1, then 2. Then, for the next part of the sequence, I will take everything that is here, hop, I copy-paste here, and then I take the 4. But at the end, that's all the number that is in my sequence. OK? Does it make sense? Yes? To allow smoothly to increase the number of restarts. But it's one kind of restart schedule, although you can use a geometric sequence, for instance. But this one is commonly used because it allows to increase the number of restarts, but also to come back to few number of failure.
Okay, so 1, 1, 2, 4 means in the third
Yes, that's the number of failures that are allowed. And when you have reached this number of failures, you go to the next number. So for instance, I am here. I have allowed 4 failures in my search. After 4 failures, I go to the next number. OK, now I will allow 1 failure. And I continue, I continue, I continue. OK? Until your timeout is exceeded. Yes? Very good question. In the simplest version, you restart everything from scratch, but you also have implementation where you store some information. For instance, when you use heuristic like impact-based search or activity-based search, you can store information that will be used to do not make the same decision or to improve a little bit, try to do some kind of online learning. OK? Yes? Oh, yes, you're totally right. We restart only when we have some stochasticity in the selection. If it is deterministic, there is no way, no sense to do restart. It can be done because you have a probabilistic heuristic, or here when also you learn information online. OK? OK. That's all for the CP solver. There's a lot of the things to say, but it's really a standard CP. Other question for that? OK, now let's move to something that is new. Generic representation function. So our goal here is to leverage learning algorithm to speed up solving process. For instance, here a value selection heuristic, but at the end we want to do also other things. And the observation is that CP solver can handle many optimization problems. You have a solver for routing, scheduling, assignment. And for a practical use, if I want this to be used for anyone, I don't want them to code by themselves the neural network architecture for each problem they use. So I want the learning component to be generic for any kind of combinatorial problem. And the idea here is to build a function that is able to encode any combinatorial problem into a structure that is dedicated, that is suitable for learning. And so the first question here is, what are the requirements for a function? And to answer this question, we need to think about what a CP solver is able to handle. So we need to be able to handle variables with different kinds of domains, so integer domain, set domain, interval variable domain. We want to be able to encode any kind of constraint. So we have a linear constraint, but we want also to be able to tackle global constraint, table constraint, any kind of constraint, actually. Also able to handle problem, whatever is the number of variable, whatever is the number of constraint, and whatever is the number of value. And also, we want to preserve the combinatorial structure of the problem because we believe it's important to learn something that is meaningful. And last requirement, we want the function to be bijective. So it's a fancy way to say that, OK, I have my combinatorial problem, I have my encoding, OK, I have my representation. Now, if I decode my representation, I want to go back to my initial problem. OK, so the function must be bijective, one-to-one matching. And the question is, how can we build a function, such a function? So what we propose here in the CP paper is to encode the problem as a labeled tripartite heterogeneous graph. So what does it mean? So you will see it's very simple. Heterogeneous means that we have a graph with a node and edges, but where the edges and the node can have a different meaning. Tripartite means that we have 3 different meanings for the node. And labeled means that we can add information, so feature for each node or also each edges of the graph. And so to give you a concrete example, here is how we encode this CSP. So here you have the variable with the different domain, and here 3 constraints. So 2 inequalities and 1 all different. So the encoding, first, you will see it's very intuitive. I have 3 sets of nodes, V3, V1, and V2. 1 set of nodes for the variable, 1 set of nodes for the constraint, and 1 set of nodes for the value. So one vertical, okay. And then for the edges, I will add one edges if a variable is involved in a constraint. For instance, x1 here is involved in C1 and in C3. And indeed, my node here corresponding to x1 is linked to C1 and C3. Okay? And then I have one edge if a value is included in a domain of a variable. So now, if I take x3, oh no, not x3, it's not very interesting, x2. If I take x2, okay, I have the value 1 in the domain and value 2 in the domain. Okay, that's the encoding that we propose. Okay? Okay, what about the feature on the vertices? And something that is quite nice is because here you have node with different meaning, you can add different kind of feature for each node. So here what we did, feature for the variable, we add the current domain size, the initial domain size to see what has been current, if the variable has been already assigned, or if the objective is to optimize. So that's very simple variable. There are a lot of room for improvement here by improving the features that are added for each node. For the constraint, we add the constraint type as a one-hot encoding, and also if the constraint has been useful to reduce the domain through propagation. And for the value, only the numerical value. So very, very simple. You saw on the talk of Lars that we can find very, very more useful features. So here it is a first attempt, but it can be improved for sure. Okay, and so finally, here you have the complete formalization of the encoding with the different set and function. So conclusion for that, the goal was to encode a CSP or a COP in a generic way. The inspiration for that, we took the inspiration from the work of Maxime Gass for mixed integer programming, where there they propose a bipartite graph because in a MIP, you don't have any kind of constraint, you only have a linear constraint, so there's one kind of node that is not required. And so here we extend it for constraint programming in any CSP. And also what you can do to extend is to add new feature to this representation. And small disclaimer for that, this representation is not perfect. I will discuss then few drawbacks and few challenges related to that. Yes, Leo?
In this representation, the bipartite encoding, what kind of thing you have? You have just variables and values, and they're connected?
Variable, constraint, and the value are binary. So in the edge, you know if it is a 0 or a 1, if I remember well. But yes, you have one node, kind of node for variable, and one node for constraint, but one node for a specific for each constraint. But you don't have one hot encoding because we have one kind of constraint. Okay. Question? Yes. Very good question, and actually, constraint programming solver struggle with continuous variable because the goal of CP is to explore a discrete state space. Here, if your solution space is not discrete, it's much more difficult. So what you can do, what the CP solver can do is to discretize. I don't know if there are other techniques, maybe Tayas, you know for that. But generally speaking, yes, CP is not the best tool for a continuous problem. Yes?
So the value nodes that we have the V3.
Yes?
I'm just trying to understand. So let's say X1 takes only 3 values, 1, 2, and 3.
Yes.
So there will be 3 nodes in V3, and X1 will be connected to all of them. Is that how it's represented?
Yes, so here, maybe I can show you the other slide here. So here I have one node per value that is on all the domains. So I take the union of all the domains. I look what are all the possible value. So it is a node per possible value. And if my variable has this value in the domain, I use our edges. It's dynamic. Yeah, yes. It changes during the propagation. I will talk a little bit after about that. But during the propagation, you will remove domain from the value. And then when the domain is not, the value is not anymore in the domain, you don't have this link anymore. And so the graph changed dynamically during the search. Okay? Okay, now the learning part. So the learning agent that is based on reinforcement learning and graph neural network. Okay, so we are here. We have the representation of my current CSP on a given node of my tree search. Okay, and let's say I want to branch off X1, for instance, using the first fail principle, which is a variable selection heuristic that is quite common in constraint programming. Now, I will call my model using some training data to tell me I want to branch on value X2. How can we do that? It seems to be not so easy, and indeed, here is the architecture that we propose here for that. So I will explain now the different aspects of this architecture. Okay, so that's the neural network, and then also the training with reinforcement learning. Okay, so the neural architecture. So first part is this the encoding. That's what I presented in the previous slide using the label tripartite heterogeneous graph. First step, it is a graph neural network. That's a graph neural network that will take this graph as input and will give you, for each node, what we call an embedding. An embedding is just a vectorized representation of a node. So I compute an embedding, a meaningful way, and a hidden way, to give you information for a node in a vector. Okay? So I have embedding for each node, so I have an embedding for my variable node and for my value node. And then I have a fully connected neural network that will take my first embedding, my second embedding, and tell me, okay, for this variable and this value, how good is this branching? Okay, so I estimate the most promising value using a fully connected neural network. And finally, when I have this, I have my branching selection. I use the score to branch. Okay? And for the learning, we use deep reinforcement learning. And for that, we need historical or synthetic data. But unlike supervised learning approach or imitation learning, you do not need to solve the problem a priori. Okay? So you don't need to do that. It can be very, very difficult if you have a larger problem. If you have this kind of signal, as Walter explained yesterday, I recommend also to do kind of supervised or imitation learning. If your goal is only to improve the execution time on problems that we can solve to optimality, it's better to use supervised learning because you do not have to learn how to solve the problem. But here we made the assumption here with reinforcement learning that we want to target problems that we are not able to solve to optimality. Okay, so that's why we don't have a supervised learning. Okay. So, few words about neural network. Who knows how a neural network is working? Okay, okay. Still a few people that don't know. I will just explain in one slide how does it work, and also then I will increase the complexity because the next slide is how a GNN is working. So, okay. Let's assume here I have a set of features, X, and I want to learn something meaningful from that. And here I have my neural network. Okay? The main principle of a neural network is that each neuron here, so a neuron here, will compute a linear combination of the previous layer, the information in the previous layer, followed by a nonlinearity. That's the essence of neural network. So, for instance, here I have a vector of feature as input, and I want to compute something in this neuron here that I call H11. In order to compute the information in this neuron, what do I need? I will need the information from X1, for X2, and X3. So everything from the previous layer. Okay? And how do I combine the information? Using a linear regression, a linear combination. So I have a wave theta that I need to learn, and a bias B that I need to learn also. So a linear combination, and then I follow this by a nonlinearity, a nonlinear function. For instance, a ReLU, but it can be any nonlinear function. Not any, but assuming that it is a ReLU. Okay? And theta and B are the waves that are learned during backpropagation. That's for this neuron, and what is nice with neural network is that for this neuron here, I will also use information from the previous layer, but the waves are different. So hopefully, that's something that we want. We want this neuron to learn a different function. And then I continue for this neuron, And then here I have already 3 representations, 3 information in this neuron. And in the second layer here, what I will do the same, but not from the information from the input, but from the previous layer. So we will take information from him to do a prediction, also with specific wave. So we have a lot of specific waves that are stacked like that. Okay? And we do it, you stack how many layers that you want, and at the end, you have your prediction that you want for your input. Okay? And in this case, I want to have a real value, so that's a prediction. Okay? And so the fundamental equation of fully connected neural network is really that. It is the idea. In order to compute the information for a given layer, I take all, in order to compute the information here, I take all the information from the previous layer, so HK here. It is a linear combination here that is followed by a nonlinearity. Okay? So the learning aspect, here we want to learn what are the waves that are involved at each layer. And the main characteristic, why it is working, why we can learn something, it is because all the network is differentiable. It can be trained with descent-gradient algorithm. In practice, so that's the very simple neural network, but you can add many things. For instance, you can add regularization in order to avoid overfitting, other activation function than ReLU. For instance, you have leaky ReLU. You can adapt it for other tasks using for classification if you change the last activation. So there are many, many different variants of that. Okay? Question about that? Clear? Okay. Now, what about graph neural network? Now we'll increase in complexity. Now, my input is not a vector of feature. My input is a graph. So for instance, here it is a simple graph with 5 nodes. And now what is a layer in a graph neural network? Okay, so I forgot also, for each node, you can have a set of features that you want to leverage, as I explained before. Now, the principle is that at each layer, I will compute new information for each node. So I will compute new information for this node, for this node, for this node, for this one, and for this one. And the main question is, how do I compute this new information? And so for that, what I will do, I will call an operation that is called message passing. In order to compute the information for this node at the second layer, I will use information from the node itself here. So in order to compute the information here, I will take the information from the node itself at the previous layer with some wave that must be learned, but also information from all its neighbors. And in this case, the node has 2 neighbors, him, V1, and V3 here. And so that's the part that you can see here. We have a wave here, and the wave is the same for all the neighbors. That's why it's work with many different nodes. So you are invariant with the number of nodes. But you will use information from the node. And here we have a fancy operator here, which is called the aggregation operation. We tell you, OK, I have this information from all my neighbors. How do I combine them together? It can be, for instance, the average. So you have better choice, but let's assume here we take the average. OK? So that's the first operator. I combine the information from the neighbor. And then I have another operator, which is the merging operation. OK, I have information from my current node, my neighbor. How do I combine them together? It can be a concatenation of information, for instance. OK? So I do it here for one node. But I will do the same for all the other nodes. For instance, to compute the information for him, I will take information from him at the previous layer, from him because he's neighbor, and from him because he's a neighbor. OK? Clear? And we do the same for each vertex. And then what I do, so that's one layer, I do the same, but with the updated information. So again, for him, I take information from him, and from him. So that's the second layer of my neural network. And what is nice, you can observe, I put the node here in green, is that at the first layer, this node has received information from its direct neighbor, but with the message passing, the message propagates. And now, because this node here received information from him and from him at the previous layer. Now he receives also information from the most distant node. Okay, yes? Yes, very good question, and generally we can also use a pooling layer to mitigate. But you can also use other operation than the concatenation. Okay, and then also here it is different way. So you have specific way at the different layer. And at the end, what do you have when you do this process? You have what we call an embedding, so a vectorized representation for each of the nodes of your graph. And the output, yes, it is the embedding. And so, like fully connected neural network, everything here is differentiable, and so you can train it using gradient descent. Okay, you have trainable wave involved at each layer. So that's the very simple, the most simple architecture of graph neural network. You have a lot of other architectures that are existing. For instance, with attention, you have different ways to do the concatenation and the merging. Instead of taking all the neighbor, you can take also a sample of the neighbor. That's the graph stage convolution. So very, very different implementation. Yes?
It looks as if you're not using edge information.
In this case, no, I'm not using edges because I just presented the easiest version, but you have architecture that leverage edge information. But yes, very good question. And so here, you have the fundamental equation of GNN, and that's really that. In order to compute the information of a node, what you'll do, you take the information from himself with trainable wave, and you concatenate or you merge with the information of all its neighbors. That's one layer. Clear? OK. So what are the benefits of graph neural network? I won't go into the detail for that, but I will give you 2 pointers. First one is the tutorial, the course of Petar Velikovic, which is a researcher working a lot on graph neural network, and is one of the inventors of a graph attention network, which is one of the most widely used architecture. So I recommend this lecture. And also, it's a very, very great speaker, so I really recommend this. And also, you will see, maybe you already know it, graph neural network is an architecture that is more increasingly used, or at least considered, in combinatorial optimization. So that's something, even if you don't know, use it, just to know that it's existing and how it's work. And for that also, I give you a link on a survey that I co-wrote with Elias, André Lodi, and Petar, and Christophe, and Didier, that give you a broad overview of how graph neural networks are used for different combinatorial tasks. Okay? It is on arXiv and also in journal Machine Learning Research. Okay? And on the survey, you will find, okay, this, but also something very important, what are the current challenges and the limitation of graph neural network? Okay. Still okay with graph neural network? Let's increase the complexity now. Here, I show you something for a graph that is simple. But my graph here is heterogeneous. How can I handle this? And the idea here, I show you one fundamental equation. Here, what we propose is to have a specific equation for each kind of node. And here is the equation for variable node. It can seem squarey, but actually it's very, very simple. It's really what I presented in the previous slide. So let's assume I am in this node here. In order to compute the next information for this node, what I do? I take information from the node itself, and then as I am a variable node, I have connection with constraint nodes. So I will have a specific way for my constraint node, so I take information from all my constraint node here, and also information from all my value node here. So that's really just to say that I have specific convolution for each kind of node, but that's really the same. That's really this. There is also something else. I just keep in memory, in the information, what are the initial features of my node. You can see it as a kind of a skip connection as we have in a ResNet or a deep neural network, just to keep the information of the previous feature. So that's for the variable node. For the constraint node, a little bit easier because if I look at the constraint node, I don't have relationship with the value only for the variable. So that's why I'm here. and for the value, same ID. Okay? Okay, so you have our graph neural network. And the trickiest part of the presentation is done. Now, is it over? Not yet. At that time, I know that I want to, let's say I know that I want to branch on this variable, x2. So I have an embedding. So the vector array representation of my variable x2 after the GNN inference. Now, I have also an embedding for my value. And now, it's a very easy part. I have a fully connected neural network for my first embedding, a fully connected neural network for my second embedding, and then a last neural network that combine both embedding and that at the end give me now my Q value, my estimation of how good x2 v3 is for x2. And it is this information that I will use for branching. Okay? And then we have everything, the final inference to obtain my Q value, my estimation. I take both embedding, I have a fully connected neural network, second one, and then I combine both. And then that's it. The summary of the architecture. I encode, I have my graph neural network. My tree, fully connected neural network. And last question, how do I select my value to branch, given the estimation? Different way, but the simplest way to do it is to use the argmax. You are looking at all the value in the domain of the variable you want to branch on, and you take the best one. Okay? Question about the architecture? I have a question for you here. How can we train that? So for that, of course, we'll use machine learning. I won't explain everything about machine learning. You see it on the first day of the summer school. But general characteristic of the paradigm we use reinforcement learning. We need synthetic or historical data. And as I said, I do not need to solve the problem a priori. For the training algorithm, it's deep Q learning. And in CPL, we are currently adding support for PPO, proximal policy optimization, which is a policy gradient method. For the implementation, that's something that is quite nice in Julia also. As you have in Python, we have the algorithms that are already implemented. So we use the implementation of reinforcement learning package. For the neural network, it is also implemented. We also have the graph neural network. Not the architecture like that, but we have the basic for the backpropagation using Flux. And also, as I said, Julia is a young language, so we needed to do some modification to fit our specific need. And the novelty here is not really on the reinforcement learning algorithm. We use something that is quite standard, but more on the environment that we propose for the learning. And that's what I will present now in the next slide. OK, in a nutshell, reinforcement learning, we have an agent. The goal of the agent is to obtain the most reward as possible during what we call an episode. And an episode is simply a sequence of state from an initial state to a final state. So to move to another state, the agent will do some action, and it will collect a reward, the score obtained after each action. How good is my action in an immediate way? And so when I want to solve a problem with reinforcement learning, I need to model the environment. It's like the modeling step in CP. You need to express in a declarative way what is your environment. So you need to define set of state, action, transition function, so how I move from one state to another one, and the reward function. And so that's what we did here. We defined a specific reinforcement learning model to be used inside the CP solver. OK? So here, an overview of the reinforcement learning we built. So the agent to train, it's a value selection heuristic inside the CP solver. An episode, how do we define an episode? It is a path from the root node to a terminal node. So it's only a path without the backtrack here. But we use information from the propagation, but the episode, how we define it, is no backtrack. We go from the root to the final node. Initial state, it's the root node, so it is a problem that is currently unsolved. And the final state, it is either a feasible solution or also an infeasible solution if you have all the variables that are not assigned. And the action, It's simply, OK, in my branch, do I go left or do I go right, or the value, if you have different branching, different domains. Each time I do an action, I will collect a reward. I will define the reward in the next slide. And for the transition, I do all the CP stuff. So I will branch, I will do the propagation, I will do the fixed point, I will do everything that is done in your fancy solver. So everything that can be done by CP is part of the transition function. And for the reward function, it requires a little bit more explanation. That's what I will do now. So main principle of the reward function is that the goal here, we want to find good solution quickly and not to prove optimality, because the task is much more harder. So now we are trying to find good solution very, very quickly. And the intuitive ID, what we can do here. Intuitive ID, OK, I want to get a good solution. I will use the final objective cost as a reward signal. I will use the final cost that I have at the end as the reward. What do you think about this ID, if you have some experience with reinforcement learning? So in this case, we have the reward only at the end. Only at the end, but I do not have reward signal during the different action in my tree. So if I do my first action, the problem is not solved, so I don't know exactly what is my reward. So you can have a linear separable function, but it's not always the case in CP, and most often it is not the case. So we have the problem that we call the sparse reward issue. So the proposition here, if we propose a rewarding scheme that is based on the domain reduction of the objective variable at each node. So propagation-based reward, we have the variable corresponding to the objective function. So let's assume I want to minimize this. The reward follows three principles. We want to reward the propagation of the largest value of the domain, because, OK, I want to minimize something. So if I remove something that is very high, that's good, because I want to have a small solution with low cost. Second principle, if I remove from the domain low value, that's something I will penalize, because I want the value to be as lowest as possible. So that's something I will penalize. Just to illustrate this, let's assume that at the beginning, for my objective variable, I have a domain of 10 variables, so 10 value in my initial domain. Now, I step t plus 1, my propagation tell me, OK, we can prune the three highest value of the domain, 5, 6, 7, and also value 1. So now, because I want to minimize, what I will do, I will reward the removal of this and penalize the removal of this. And so at the end, what we do is, so here we can do it in a different way, but here we just take the difference between both, we normalize with the initial domain size, and then we have the reward value. And this is not sparse, you can have it in different parts of the tree. Okay? And the last principle, we can also penalize if we reach an infeasible solution. So that's the idea of the reward. And the final reward is only the accumulated reward for each transition. And that's it. Here, the architecture behind CPER. Question on that? Yes?
I'm just very surprised by the penalty. Like the lower bound, you cannot. Every solver or every search will have to increase the lower bound. So why would you penalize that the method finds out?
It is, if you want to prove optimality, indeed, it can be a drawback. But here we want to find good solution as possible, and here we observe that we don't have issue with that. But it is not seated for each kind of problem. For the three problems that we have, we could observe that for some problem it helps, and for some other problem, it does not help, but it do not worse than the reward of simply taking the cost at the end. But for the optimality proof, I agree, it can be an issue. OK, what time is it? Time to conclude. OK, does it work? So maybe I can skip the experimental result then. So roughly speaking, important message of the performance here is that we can observe that we can get good solution more quickly than other heuristic, activity-based search, impact-based search, and random search. So we can get better solution in less number of nodes, but the drawback is the execution time of calling the neural network is a real bottleneck. So here, to explore 40,000 nodes, it takes 130 seconds. But here, to explore 44,000 nodes, it takes 14 seconds. So we have a factor of 10. We have roughly 10 times slower using the GNN in terms of speed in exploration. So that's one of the challenges we would like to address. But we are able to learn better heuristic. Yes?
So that time includes the time it takes to build your tripartite graph at the beginning?
Yes, but I think this one is neglectable because you have to build only once at the beginning of your tree, and then you can do some operation to avoid to rebuild it from scratch. But yes, it has to be taken into account. So also, it's say the same story there. Okay, so now very important slide. My second conclusion. Seems to be great because we can learn something. Should you use it for solving your problem and get competitive result? And my answer is no at all. Do not use it if you want to have good result. Use it if you know what you are doing. I mean, I believe it is an interesting research direction, and that's why I am working on that, but it is not mature yet to get competitive result. It's not mature like a portfolio selection that last presented where we can get competitive result with it. Here, it is only the beginning. I believe it is an important research direction, but do not use it if you have an industrial problem to solve and if you want to get good result as possible. And for that, it's currently better to use dedicated heuristic because it's much more easier to tune and to build. And so I think it's important to have this take-home message. It is kind of summer school because when I have a partnership with a company nowadays, they heard a lot about machine learning, deep learning, and even if they have a combinatorial optimization problem to solve, they want to use deep learning. But most of the case, it is better solved with a standard operation research method. So be careful for that, and be careful also to know what is the right tool to use. So don't use it for solving industrial problem if you want good performance. And I think we have some success story of using machine learning for combinatorial problem, mainly also on the modeling part, but for the solving it's much more tricky, and so that's why I do not recommend it, unless you know what you are doing. Okay? But as I said, I believe it is a very interesting research direction. And if you see it as a research direction that you would like to pursue, yes, go for it. But that's not what I will use as the first choice for industrial problem. But if you are able to find it, that's very, very good. I think it will be a very great contribution. Okay? So just quickly, for the 5-10 minutes, let's assume that, okay, you understand that, and you like this idea of a hybrid paradigm. What kind of research can I carry out in this field? So in the next slide, I will just show you a few challenges that we have. So this one, I already explained it a little bit. When we look at the execution time, we see here that we have an exploration rate 10 times slower, roughly. So what can we do? Few ideas. We can use caching, as I explained it. We can also try to reduce the execution time, the inference time of the model. So here we have a very heavy graph neural network with fully connected. Maybe we can use some technique of network pruning or distillation to use the knowledge in a smaller graph, smaller model, and get similar performance. And also, something that works very well in another project is instead of calling the neural network at each node of the tree search, only call them on the nodes that are the most impactful. And on our work with the decision diagram, we did so, and what works the best, it's only calling the neural network in, I think, 100 nodes of the tree search, only at the beginning, and that's what gave good result, and not calling them always. Here you have the curve when we use it at every node, and here only with some parsimonious call. Okay, rethinking the representation. So first problem, it is the scalability. So with 5 vertices for the graph coloring, you have 18 nodes. 200 vertices, you reach 4,000 nodes, so it's growing quite fast. So how to handle this? And also the expressivity. So for instance, here with the current encoding, let's say I have two inequalities with a different constant here. I can decide it to consider both as an inequalities, but there I lose the information about the constant. Or I can try to see it as two different inequalities, so lesser or equal subject to this constant, but in this case, I lose the information that both constants are the same. So how can we handle this and do not lose information? How can we be more expressive on that? And Leo is working on that in part of his master thesis. And also, something that you may ask, why do we learn only a value selection heuristic? Why not also learning a variable selection heuristic? That's something that is very, very interesting, and that's one of our further work, trying to use also this for the variable selection variable. So use first the model to train what is a good variable, and use this information also for the value. Okay, so we have this kind of synchronization between both. Okay, I'm almost at the end. Maybe you are disappointed because you wanted to see something that is working quite well. Well, it's not the case. I believe it's an interesting research direction, but not yet to get competitive result. But if you want to get good integration of a learning with, in this case, decision diagram, I saw in the poster that some of you are interested in decision diagram. This one is working quite well. Contribution here, we combine reinforcement learning and decision diagram to get better dual bound. And the main result is that we are able to beat Cplex and competitor for the maximum independent set in terms of execution time and also optimality gap. And also, very, very recent work. No learning here, only decision diagram. It will appear at Journal of Artificial Intelligence Research, where we use decision diagram, branch and bound, and WAM starting to solve a combinatorial problem. And the main result is that with this, we were able to solve, to close 15 open problems in TSP with time windows. And no learning was there. Okay, last slide, I promise. So the research hypothesis here is that constraint programming can be used as a hosting technology for building the hybrid AI. So here, really, what we did, we integrate the learning aspect inside. So we introduced CPL for that. You will have the opportunity in the lab to work a little bit with it. And what I discussed today is mainly the content for 3 publications that we did last year. Okay, thank you very much for your attention. So different contributor is not the work of myself. That's the work of a lot of different researchers and the team that we have in Polytechnique Montreal. So it takes really a lot of people to build this kind of work. So thank you for everyone. And we are also always open for new collaboration. Thank you very much.